practice ones and then one real one. But the computer system's down today, so we won't get it. So I'm sorry because it's actually pretty good practice problems. Then Wednesday I'm in California, so I will not be here. I will ask one of the other professors to substitute.
Just as long as you bring back sunshine.
Well, the term forecast, according to the meteorologists I listen to, is that we are going to have rain in the valleys and snow in the mountains. So the road should become clear down here. Hopefully build up snow up in the mountains. It's not a bad combination. So you can go find the snow if you want to go play, but it's easier for driving. So I don't think I'll be bringing the sunshine back. In fact, Central California is getting quite a bit of rain, which is very good. I have a customer down there. They're at 25% of their. It's a hydro customer. They're 25% of their normal snowpack. There's some cities in Central California that are looking at less than 68 water. They need the water area. They need the rain. Another administrative issue. Labs do start tomorrow. And for those on Tuesday, they start on Thursday. Your bound lab book, that will be in lab. So you don't have to buy a new bound book for second semester. You can use, you still need to buy the spiral bound physics 2 lab book. We will be doing almost all of our work out of that spiral bound book, and you'll get your grading out of that. Technically, it's a FERPA violation, but we haven't got the whole system dialed in. And I don't want to let go of those labs because they're really pretty good. So don't peek into other people's books. That's all. Any questions about lab or administrative issues? Any other, just general questions? Everything's working fine. That sounds good. All right. What I will do, we'll review some problems if you're interested. All right. So we've been playing with this. If we look at our 2 workbook problems, one of them says, if there was a third charge, not just the 2 charges that we have, how would we identify that third charge as being unique? If I said the third charge was attracted to a positively charged object, and it was attracted to a negatively charged object. Would that be true if there was a new third charge?
Not necessarily. It's also true for neutral charges.
It's also true for neutral charges. So that's not conclusive. If you look at it.
Although also, would we not know how a third charge would behave should said third charge exist?
That is true. We're going to assume it acts like the first 2 charges in the sense of what other property would we expect. So normally like charges repel each other. So if we had a third charge, it would repel, if we had 2 objects with that third charge on them, those 2 objects would have what kind of force between them? Force of repulsion. That's the conclusive. The 2 objects with that third charge would repel each other, and they would be attracted to a negative and positively charged object. Then, the next thing we looked at, we played with this, we looked at the charge model, and what the example was in the textbook, we can look at the electroscope. Is the electric scope as a whole positively, neutrally charged, or negatively charged right now? Does it have a glass rod charge? Neutral. How can that separate? How can the leaves separate if it's neutral? Thank you. What was wrong with it?
There's actually 3 different power switches.
Oh.
So there's this one, and then that one. There's have to be others.
All right. The back didn't light up at all. What's that? Yeah, we'll get it registered. Why don't we go ahead and go with class for now, and then we'll get to those in a bit. So, electroscope is neutrally charged. I rub the glass rod on the silk, and now nothing's happening. There we go. Now, I move it away. It's neutral. Let's go ahead and now put the glass charge on the electroscope. It's not transferring very well, is it? If I bring it glass rod closer, is the electroscope glass charged, neutral, or plastic charged? Glass. If I bring glass charge next to it, what will happen to the leaves? They'll move further away. The charge model, would you all be able to know what to draw? Now, if I bring a plastic charged object near the electroscope, what will happen?
It'll be attractive.
I think it sparked over. So as I bring it closer, what happens to the leaf? It becomes closer. Now, when I touch the sink, what am I doing?
Grounding yourself.
I'm grounding. What is grounding? So when I touch the ground, this piping actually goes to the earth. It goes to the ground. The earth's rather big. So when I touch this, I become a conductor. I'm not a great conductor, but I'm still a conductor. The extra charge can leave the electroscope, it flows through me, throws through the pipe, and then spreads out over the whole planet. At that point in time, is there any question about what's happening there? Any question about grounding? Now, let's start thinking about fields again. We talked about a gravitational field last semester, not in a lot of detail. And we're now talking about electric fields. How would we detect the presence of a gravitational field? Josh?
We can see its effects.
We can see its effects. Let's see, does this work? I'm going to take this mass. Was it in a gravitational field? Is it in a gravitational field?
Mm-hmm.
How can we tell?
It,
What's that? It fell. It started to accelerate, didn't it? If there's no gravitational field and I let go, what would happen?
You just sit there.
Nothing, right? There'd be no net force, assuming there's no other forces in it. So I'd let go. Now, if I put this on some kind of spring balance, or some kind of spring scale, and I knew the mass, at that 1 kilogram mass, what force would I expect that field to be exerting on that 1 kilogram mass? Of a 1 kilogram mass right here. Wouldn't it be 9.8 newtons? If I added 2, right? If I took it to the moon, would you expect that scale to still say 9.8 newtons? No, because the gravitational field is not as strong. So I could go around to different places in the universe with my 1 kilogram mass and my scale, and I could measure the strength of the gravitational field at those different points in space, couldn't I? Now, which direction would the force point on my mass if I was right here? Straight down, right? Straight down towards the center of the Earth. So we can get 2 pieces of information by measuring the gravitational force on that mass. That suggests an approach to find the electric field on measuring the electric field. What could we do to detect an electric field? Would we use masses? Use a charge.
Charges.
We would use a charge. If I had an object here with a 1 coulomb charge, and we found out that force was pointing in that direction, what would that tell us?
Either there's a negative charge in that direction or a positive charge in the direction.
Right? It could be a negative charge up here that was attracting it, or a positive charge down here, which was repelling it. So the electric field would be the same in either case. The field would be pointing in this direction. We'd have a charge. And the force on it, on that charge through the electric field, would be in some direction. So let's look at things. I can get this up and we can use PowerPoint. Do people want to try a PowerPoint free lecture? Just to see? I hear you get it. So with gravity, we have some force on an object M. This is on M. It's due to that mass of that object times the gravitational field. G at this point is also down. Force, mass, force on Q. Anyone want to guess which direction that will be, or what that will be equal to? Instead of mg, it'll be, instead of mass, we'll have another charge, which we'll call Q. And instead of our gravitational field, we will have an electric field. If we wanted to determine Q, we could say, or we wanted to determine the field, we could have a test charge Q. We could measure the force if we knew the amount of charge Q Q, we could then determine the electric field. So far, so good? In general, would you expect the electric field at every point in space to be the same?
No.
No. In fact, the electric field in general is different at every point in space. As we get nearer to a charged object, what would we expect to happen to the strength of the field? Stronger. As we move farther away, this whole idea of a field being at every point in space becomes kind of confusing because there's a vector at each point in space that describes that strength of that field. And can we draw a vector in a point? It doesn't have any dimensions. So there tends to be some confusion when we draw fields. We had 2 points in space, A and B, and the electric field at point A looked like this. The electric field at point B looked like that. Is that possible? Can we think of a good explanation of the single charged object which could explain those two fields? The field at those 2 points? That's one field. But I'm going to do actually something a little different. There's a slight problem with this picture. Let's make this one a little shorter. And this one a little bit longer. That'll work better. What would explain field? What's that?
They want to try to do a charge before the lines intersect.
Exactly. Did everyone hear that? Imagine you put a charged object there. Would it explain those two fields? Now, the charge, if it's positive, then the force is in the same direction as the electric field. So imagine that this is a positively charged test charge. It's attracted to that point. The positively charged object is attracted to that point. What would be the charge of this object down here?
Negative.
It'd have to be a negatively charged object. Does everyone see how that works? Why did I come back and make this vector longer than this vector?
It's closer.
Because it's closer.
Closer. If it was shorter, it wouldn't work, would it? Because we found that our experience is the farther we are from a charged object, the weaker the field. Now, what if I drew a field that looks like this? Is that possible?
Not that the presence of spot.
Can we have a field that points two directions at one point? We can have two different components, and there could be a net charge. But if I said the electric field pointed at two different points, if these were not components, but it actually pointed in two directions at the same time, that doesn't make sense, does it? Now we can say there's two components, maybe, and that the sum looks something like this. But there's a distinction between saying there's two components of the force and they add up to a net, and saying there's actually a field at those 2 points that points in 2 different directions. That doesn't make sense. Now, do we know the field strength here? If we're correct that there's a single charge that causes it, we could make a pretty good guess as to where that goes. So if there's enough, if we're told that this field was set up by a single charge, then we could say, well, it's probably pointed in that direction, and it's probably larger than both of those because it's bigger. But if I didn't tell you for sure that this was charged by 1 point, you probably don't have enough information. Now, with what I've said so far, is that possible? Does this mean that the field's pointing in 2 different directions at this point? No. Do we know anything about the field here, or here, or here? Nothing. No. This vector only tells us the field strength at the point. So that gets a little bit confusing. So at every point in space, if this was in fact the source of the charge, there would be vectors that would indicate the field. There's an infinite number of field vectors. Now we can't draw them on a paper, it would make a mess, right? The key point I'm trying to get at is the field encompasses all space. At every single point, the infinite number of points in space, there is a field strength. It has a magnitude and a direction. So when we start to think about this in 3 dimensions, it's a challenge to visualize. Everyone comfortable with our projection?
So how then would gravity affect the electrical field?
They're completely independent. Well, at this level, they're completely independent. Okay? We're going to stick to relativistic, non-relativistic speeds and dimensions that are normal. Life's much nicer. This field concept is very, very powerful. We introduced it with gravity. We're going to expand on it. Now, what I'd like to do is make the connection between this and Coulomb's law and do some examples with Coulomb's law. And then we'll bring that up and so we can start to do some demonstration. Coulomb's law can be rewritten
There's a U after
There we go. We're going to rewrite it ever so slightly from before. We're going to say the force as a vector equals K Q1 Q2 R squared make sure I'm consistent with how I'm we're going to say the force on charge 2 is equal to this constant times the products of the charges divided by the distance between them squared times the unit vector from 1 to 2. So what's important here is we've now gotten rid of the magnitudes, and we want to think through all the different possibilities of charge. So this could be positive or negative, this could be positive, negative, and what does R hat mean? Do you remember what R hat means? The unit vector in the R direction. We had, how many people are comfortable with I hat and J hat? I hat's one in the what direction?
X.
J hat's one in the
Y direction.
and R hat, one in the
R direction.
R direction. We have two charges, Q1 and Q2. What direction would be R1 to 2? R hat 1 to 2.
From 1 to 2.
Well, we can draw R 1 to 2. And it is in the direction from 1 to 2, isn't it? R hat would be length 1 in the other direction. So let's look at this now. K is positive. Q1 and Q2 are both positive. R hat now is in this direction here. We now have a magnitude of the force. Is that positive or negative? Positive, positive, square, that's going to be positive. So we have a positive times R hat. The force on Q2 will be in that direction, in the R hat direction. Does that make sense? You have like charges, so the force should be one of propulsion. What if Q1 and Q2 were negative?
Same. As long as it's both negative.
Well, now if we look at our equation, we have a negative times a negative gives us a positive. So this, the magnitude is still positive. Or this, it's not exactly going to be a magnitude. It's a component. This component in the R direction is positive, and it's in the direction of R hat. What if Q1 or Q2 is positive and the other is negative? Now this component becomes negative, and the negative R hat direction so we'll have the magnitude of our force in the negative R hat direction. Does that make sense? The force on Q2 is in the negative R hat direction. Now what if we wanted the force on Q1? Now we'd have to draw R hat from 2 to 1, and everything changes direction again. Does everyone kind of see how that works? Okay. So that's the convenience of choosing positive or negative. Is it important, would this equation work just as well if we reversed the signs and said that protons had a negative charge and electrons had a positive? The math would still work. All right, so any questions about this? Do some practice. Now, let us say we want the electric field. You can rewrite this a little bit now and say this is equal to Q2 times K Q1 over R squared times R hat 1. to make this look like the problem up here, can we say this is equal to Q2 times E? That implies that we can calculate the electric field using this equation. So once we have a reference point, once we establish our coordinate system, we can figure out the direction.
For the part of that, if you go from Q one loss on that,
I'm going to let what we've decided was that the force electric on Q2 was equal to the charge Q2 times the electric field at point Q, at point 2. So for that to be true, then by factoring this must be equal to that. Thank you, James. Any other questions? So what I'd like to do is practice some things. All right. I want to write some steps down for solving problems. So what we're going to do is I'll write the steps here, I'll write the problem here. I want to know the force on the 10 nanocoulomb particle. Let's go through the procedure that I'm going to write over here. We see how it works. And this is slightly different from the way Knight approaches things. If you want to approach things the way Knight does, this is fine, but I really like, obviously, the method I'm teaching you. Step one is draw. So 2 is our charge of, what do you call, oh, this is important. We draw from the source charge to the point of interest. In this case, I want to know the force on the negative 10 nanocoulomb charge. So he's the one that's of interest. So we're going to pretend that he's not there in terms of what's causing the electric field. What we're going to do is say, if I'm looking at a charge in a field, I'm not going to consider the field created by that charge. Just like when I'm looking at the gravitational force on the remote. Do I worry about the gravitational field caused by the remote? No, I look at the gravitational field caused by everything around it, the Earth, and then I see how that acts on this mass. So I'd say this is the mass of interest. In a similar way, since this is the charge of interest, and this is going to be considered my source, I will draw R from, and what is R now? From there to there. The first part really is who's the source, who's the charge of interest. Once we figure that out, draw for each source and each charge of interest, vector R from our source charge to our charge of interest. Step 2, determine R in meters. The biggest causes of problems on tests and homework is forgetting to convert from centimeters to meters. So in this case, what is R in meters? 0.03 meters. Is this a vector? Is it a unit vector? Is it a magnitude? 3. Determine theta or R hat. I should say theta R or R. In this case, let's go ahead and set our axes here. Let this be X. Let's let this be Y. What is theta equal to in this case?
0.
0. We're measuring counterclockwise in the positive x-axis. Theta equals 0. Or we could say that R vector equals 0.03 I hat meters. Is everyone comfortable with that? Step 4 will be to determine R hat. We can do it 2 ways. We can say R hat or we can say it's equal to R vector over R magnitude. In either case, we end up with what? So now we really have everything that we need inside this equation, or if we wanted to determine the field inside this equation. We have force equals K, which is 10, what is it? 9 times 10 to the negative. Anyone have that? 9 times 10 to the negative, positive.
9.
9 times 10 to 9?
Yeah. 9 times 10 to the 9 Newton meter squared cubic squared.
9 times 10 to the negative 9, thank you. 9 times 10 to the 9 Newton Coulomb squared meter squared times. Thank you. Meter squared over Coulomb squared times Q1. 10 times 10 to the negative 9 coulombs times 10 negative
R hat is I.
In this case, I've gotten rid of the absolute values, and the direction should be correct.
Why is it?
Isn't it I?
I had, thank you. I, J.
All I know is
Frankly, I don't know why they chose I and J.
What's that?
I and J seem very similar to be putting it so close together.
It will happen long before I came about. If I'm really being careful, I will put a little tail like that on my eyes, and I'll make my J's to make them very unique.
Should we use iPad or like X hat?
There are some books that use UX hat. They use, so there's, one notation I do like a fair amount is they'll say UX, U being the unit vector, UI, UR. But IJKs pretty much take it over.
Will you allow us to use those on the test?
I'll pick it up. If you use UX, UA, UI, UR, I'll manage.
Okay.
Does that seem pretty straightforward? Does someone have a calculator? Actually, I might have a calculator. No, I don't.
So in the end, that's K times Q1 times Q2 over R squared times.
Let's look what happens with units. Coulomb squared cancels with coulomb times coulomb, meters squared cancels with meters squared, and we're left with newtons, and we end up with a negative I hat direction. So it makes sense that the force on this object is in that direction? Yes? You can see we have opposite charges. There are charges of attraction, so the charge on the negative 10 nanocoulomb force is to the left. Real quick, let's have you repeat that process. Imagine we have now, something like this is the y direction, x direction. Our negative 10 nanocoulomb charged object is here. We have a 1 nanocoulomb object here. And now 1 centimeter apart. Would we expect the magnitude of this force to now to be greater than or smaller than the magnitude of the force up there? Let's see, let's look at it in terms of distance. The distance is 1/3 as much, right? So would that make the force, just looking at the distance component, if these two charges were the same as the two up there, by making the distance 1/3 as much, what will that do to the force? It's closer. Will the force be bigger or smaller?
Bigger.
Bigger will be 3 times bigger, 9 times bigger, 27 times bigger, 9 times bigger. It's 1 over the distance squared. So the force would be 9 times bigger because it's closer. But the charge here is different. The charge is 1/10 as big. So what will that do to the force?
Decrease it.
With a smaller force, smaller charge, there should be a smaller force. It will be 10 times smaller, 100 times smaller,
10 times.
10 times smaller. So the force here will be 10 times smaller due to the reduction in charge, 9 times larger because of the reduced distance. So the force would be slightly larger. Right?
Slightly smaller.
That can be slightly smaller. 9/10 is smaller than 1, isn't it? Alright. So go through that process. Let me get the iClicker up and do the registration with Has everyone done that?
Would theta be zero?
What's that?
Would theta be zero or
90 degrees.
Speak louder.
would theta be zero?
All right. There's two choices for theta here. Let's see. First, let's go ahead and go over this. Who's our charge of interest? Here, we're going to let this be charge of interest. And this is now our source. So when we draw from our source to our charge of interest, we're pointing down. If we measure counterclockwise, that would be 270 degrees. Or some people prefer negative 90. So let's see. Let's go ahead and go through our steps though. We've drawn R. Our magnitude of R is 0.01 meters. Our theta equals 270 degrees, or R hat equals negative J hat. We find cosine of 270, that is 0. Sine of 270 is negative 1. And last but not least, our force now would be 9 times 10 to the 9 Newton meters squared, Coulomb squared, times 110 to negative 9 coulombs times negative 10 times 10 coulombs all over. Now, let's check our signs. We have a negative here, times a negative would give us a positive. Let's see, what direction do we expect the force to be on this negative 10 nanocoulomb charge, our charge of interest? They're opposite the charge, so we'd expect it to be an attractive force. So, positive J direction, does that look good? Our negative J tells us the force is in the positive J direction. We look here, the opposite charge, the force of attraction. We expect the force in the 10 nanocoulomb to indeed be up. So that makes sense.
Question, why is it 270 degrees and not just 90? Isn't that negative?
We measure, when we're measuring theta for these, for our unit vectors, always start at the x-axis and always go counterclockwise. So we can say it's 270 degrees measuring counterclockwise. You could also say negative 90 degrees because we're going opposite of counterclockwise. So we're going to measure angles as being positive from the positive x-axis.
So is the positive charge at 0, 0, or is the negative charge at 0, 0?
You can do it either way.
Okay.
So, but we do look in the positive direction. If we look at this vector here, it's going straight down. R 1 to 2. Yeah. So start here and measure around. Moving in the counterclockwise. Start at the positive x-axis, move in the counterclockwise. If you're uncomfortable with that, you can always say that R equals vector equals 0.01 negative 0.01 j hat meters. So this is the alternate way of doing it, Eric. R is moving in the negative j direction, is it not? So we can say R vector is equal to negative 0.01 j hat meters. R magnitude is 0.01 meters, so we can say R hat equals R vector over R equals negative 0.01 j hat meters over 0.01 meters. Meters cancel, left with negative j.
So
Either method works.
would the actual physical answer of that equation just be like number newtons, or number j hat newtons?
This one here?
No, that final.
Well, let's check our unit. We have meters squared up here, we have meters squared down here, actually that should be inside. So meters squared cancel. We have coulombs times coulombs, that's coulomb squared, that cancels the coulombs, we're left with newtons.
Yeah,
So the force that's occurred.
and the j is still there.
The J is still there. And we have, in terms of direction, we have a negative and a negative. Positive, so the force is in the positive J hat direction.
And did we just take the charger picture?
No, if, let me get this up so people can. What if you look at the power, oh, that's interesting. If you look at the PowerPoint, I said I want to know what the force is on the negative 10. So I'll tell you. So somewhere along the line, we need to figure that out. Now, the last thing I did in the PowerPoint is I gave you this problem. Let's see, this was 10 nanocoulombs. And I asked what the force was on the negative 10 nanocoulomb charged object. Does that look familiar? But look at this, isn't that the first problem? And wasn't that the second problem? What we can do is find the two different components of that force that we just found. We can find this force plus this force gives us the result of this. All right, we are out of time already. Do people like it better this way? What's that?
I like the PowerPoint.